Hello, everyone. My name is Moise Blanchard. I'm currently a postdoc at Columbia, and I'll be presenting some of my work on the Oracle complexity trade-off with memory for feasibility problems, which are problems that are very much related to convex optimization. Okay, so starting with some motivation, obviously there are lots of different criteria that we could use to characterize the efficiency of learning algorithms. Perhaps the most classical one is to think about convergence rates. In this talk, we'll care also about memory. And the whole idea is that if we can understand trade-offs between these different objectives, potentially this can also inform the design of algorithms. All right, so there has been a growing interest in the community to try to understand learning with some types of information constraints, whether it be communication constraints, streaming algorithms, etc. Perhaps most closely related to this work would be works on limited memory. And just to give an idea of the flavor of types of trade-offs we're looking for, one of the very foundational papers in this line of work, memory trade-offs, was by Ranraz in 2016 for Pareto learning. So what is the problem? The problem is you need to find an unknown n-bit string x. And what you have access to are samples AI, BI, where AI is also a uniform n-bit string, and you observe the dot product x times AI modulo 2. So what he showed is that an algorithm essentially has to do, either has one of these two behaviors. Either you need quadratic memory in the number of bits n, or you need to use an exponential number of samples. And it's not too hard to convince yourself that there are algorithms in each case. So if you have quadratic memory, essentially what you can do, for example, is to do Gaussian elimination, memorizing n samples, for example, a big O over n samples. On the other hand, if you just have linear memory, what you can do is just trial and error and try to exhaust all possible values of this n-bit string x. And this would give you a number of samples that is exponential in n. However, you used the optimal memory, which is linear in n. Okay, so these are exponential trade-offs between memory and Oracle complexity for discrete problems. And what we're going to try to do here is try to have such separation between memory and convergence rates, but for continuous problems. So let me define them. The first one is the very classical first-order convex optimization, where you have to minimize the convex function f. We just assume it's Lipschitz, so non-smooth. And the goal is to find a point within these epsilon minimizers in terms of function value. What you have access to is the oracle, first-order oracle, which gives you the function value and the gradient. Okay, so this problem is very closely related to the so-called feasibility problem, which will be the main focus of this work, in which the goal is to find a ball within an epsilon radius, a point within an epsilon radius ball. So you can think of this as being the feasible set, little ball. And what we have access to is an oracle, which is a separating oracle, meaning at each query x, either it tells you, okay, the point is within the feasible set, or it gives you a separating hyperplane between x and the feasible set. So first remark is that feasibility problem is a generalization of a convex optimization in the sense that if you can solve the feasibility problem, then you can definitely solve convex optimization with the same number of oracle calls. Why? Because the gradient oracle in first order optimization actually gives you precisely a separating hyperplane, oracle for the set of minimizers. Okay, and so the question here would be how many calls to the oracle are needed. And in standard theory, there are two types of algorithms that can be used, which are very famous and very classical. So the first one will be gradient descent type of methods. So it's very simple. We start from some point and then we follow the gradient. These are widely used in practice, largely viewed as very practical. They only require updating one vector at each iteration. So its memory usage is linear in the dimension d, and also its runtime per iteration. However, in some regimes, they don't have the optimal Oracle complexity. As you can see here, essentially the accuracy decays polynomially in the number of iterations. Methods that are known to achieve the optimal Oracle complexity are so-called cut-in plane methods. And what they do is they keep in memory they keep track of a region where the optimum can be. So for example, you can initially it's the whole set, and then you can query the center, some notion of center. Once you have access to the separating hyperplane G0, you know that the optimum is not going to lie in this whole half region here. So you can safely remove it, and then you can iterate. So you query some notion of center, and then you can cut like this. So these achieve the optimal Oracle complexity. Essentially, what this is doing is some sort of binary search into dimensions. So you only pay a logarithmic price in the accuracy that you want, up to a factor d. However, they are largely seen as much less practical because runtime per iteration is much higher. Essentially, what you need to do is to remember all different cuts you did before. And because there's going to be roughly d iterations, that means that you need to store a whole matrix, which ends up being quadratic memory usage in the dimension. Okay, so we have these two algorithms. The question we're gonna try to answer is, what is the trade-off between the two? And here I specified this regime here, epsilon has to be sufficiently small. The reason being that if that is not the case, essentially we're doing less number of iterations on the dimension, and then you can show that essentially gradient descent is already optimal also in memory. Okay, so conveniently, we can summarize past works and results in this 2D graph. So we have on the x-axis memory and the y-axis our complexity. As you can see, we have these 2 points here, gradient descent and cutting planes. Cutting planes uses the optimal Oracle complexity, but uses more memory, quadratic in the dimension. On the other hand, you have gradient descent that converges slower, so has higher Oracle complexity, but it uses linear memory in the dimension, which you can also show is also optimal. The reason being that you at least need to be able to output the solution vector, which has to be with precision epsilon. So d log 1 over epsilon is the minimum number of bits you need to do that. Okay, so in red, I will represent things that are essentially lower bound, so impossibility regions, and green are the possible regions. So the first result was this breakthrough paper by Marston, Sharansi, for Valiant that essentially showed that there is memory does play a role here, meaning you cannot be both optimal in Oracle complexity and in memory. So they show this impossibility result, so this lower bound trade-off, which was later generalized to go all the way to cutting planes. And here I represented in red lower bounds for randomized algorithms. And in pink, we have the lower bounds for deterministic algorithms. So the conclusion here is that if you want to have the optimal Oracle complexity, then you need to use quadratic memory, just like cutting planes. Essentially, you have 2 log factors. I just want to mention in terms of positive results. So here, I just talked about lower bounds, but in terms of upper bounds, there has been this paper that showed that essentially you can shave off a factor log d. We can replace a log d in the memory by log 1 over epsilon. So this is more significant as the accuracy at epsilon is small. If the accuracy is just polynomial indeed, then this is just a constant factor improvement. But quite remarkably, if epsilon is really, really small, so for example, think of it as exponential accuracies, which is not a practical regime, but still, then this shows that you can already significantly improve over gradient descent. Okay, so you don't pay an Oracle complexity polynomial in epsilon. You pay an Oracle complexity that depends on the logarithmic, on the logarithm of it. Okay, of course, there is a dependency in D. Okay, so this is for exponential accuracies. What we will care about are more reasonable accuracies, more standard standard regime where epsilon is not exponentially small in dimension, for which there is still this big separation between what gradient descent can do and the corresponding lower bound. So importantly, there is a huge gap because gradient descent has polynomial in epsilon accuracy or complexity, whereas all the lower bounds that we have only depend only grow as log 1 over epsilon. And the reason for that is that essentially the price that you pay in terms of the lower bound is only a small polynomial in D. Okay. So our goal will be to bridge this gap, and this is our main result. In our work, we try to have these trade-offs that go all the way to gradient descent. And so importantly, these are exponential trade-offs because we go from Oracle complexity that is logarithmic to something that is polynomial in epsilon. Okay, main disclaimer is that this only holds so far, the analysis only holds for feasibility problems, which as we saw before is a harder problem, but they are very much related. So hopefully this can help future work to try to generalize these lower bounds for complex optimization. Okay, so as you can see, there are two bounds. The first one is for deterministic algorithms in pink, and this one goes all the way to cutting planes. So it's a trade-off that goes from gradients into cutting planes. And for randomized algorithms, it doesn't go all the way to cutting planes. So to write everything properly, so here is the formal statement. As I mentioned before, we care about accuracies epsilon that are in this reasonable regime, where it's not exponentially small, and also it's sufficiently small, it's smaller than 1 over square root e. In that case, we show that an algorithm uses this number of bits, or if it's deterministic, makes this number of queries. So here I highlighted the main term, which is 1 over epsilon squared. You can check that if delta equals 0, which corresponds to the case where you have just linear memory, then this exactly gives you the oracle complexity of gradient descent. And if you have a bit more memory, then the exponent here interpolates exactly the amount of queries that you need. Okay, it's here. All right, so these are the lower bounds for deterministic algorithms. For randomized, we have the following, where the exponent here in terms of in front of epsilon minus 2 is slightly worsened, and you can check that this only gives non-trivial lower bounds if this delta parameter is between 0 and 1/4, which explains, which essentially what was shown in the figure before, that the lower bounds don't go all the way up to cutting planes. So a few remarks. In both cases, it says that gradient descent is always Pareto-optimal up to log factors for this feasibility problem. And perhaps more importantly, for deterministic algorithms, this gives a strong exponential phase transition for the query complexity. If you have less than quadratic memory, this tells you that you must have a oracle complexity that depends polynomially in the accuracy that you want, epsilon. And this is in contrast to if you had quadratic memory, in which case you can have an accuracy, an oracle complexity that depends on log 1 over epsilon, because we know that cutting planes does this. All right, so in the remaining time, I wanted to give a few ideas about the proof and the construction of our lower bound hard problems. This is done through multi-layer, and each layer essentially is having multi-layer essentially will help us having exponential lower bounds. So we fix a parameter p, which essentially is going to be the depth. And what we're going to do is we're going to sample p dimensional subspaces, each of the same dimension d over 2p. And now we can define the feasible set, which is going to be this. So there are three terms here. The first term is essentially just a trivial term. It just restricts the search to the unit ball. And I forgot to mention that all of our problems are going to be restricted to the unit ball just for simplicity. So this is not really a constraint. The second one is also not very important. What it's saying is that we just want to make sure that the origin is not in this feasible set. That's all. The last term is perhaps the most important one, which has to do with these with subspaces that we sampled. Okay, so what this is asking is that your query needs to be approximately orthogonal to each one of these subspaces. And we're going to view each one of these subspaces as one depth. So we're going to say, for example, a query passes all the queries of depth p if it was approximately perpendicular to all the subspaces of previous depth. Okay, so here is a strategy to try to get exponential lower bounds for this specific feasible set. What we're going to try to do is to make sure that whenever an algorithm is trying to make queries at depth p plus 1, in order to do so, it first needs to visit lots of different dimensions, lots of different queries at the previous layer p. And the idea is that because they need to be also at depth p, meaning they have to be perpendicular to the previous subspaces, This is a constraint that potentially the algorithm doesn't have enough memory to store all of these constraints here. So the number of dimensions that they need to explore would overflow the memory that they have. Okay, so just to mention a few challenges, the first one is that we have to make sure that whenever we're implementing the separating oracle, that these responses from the separating oracle reveal little information about each one of these subspaces. And the second thing is that since we're looking for exponential lower bounds, we're going to essentially try to make sure that the algorithms recompute things over and over again. So the algorithm will always have some amount of memory that it can keep about each one of the subspaces. Okay, so far we only defined the physical set. To define the hard class of feasibility problems, we also need to define the separating oracle, which is going to have this form. Okay, so the first thing is that every time we are querying the separation oracle, we don't want it to reveal too much information about the subspace EP. So what we're going to do instead is we're going to store some so-called probing subspaces. So these are subspaces of low-dimensional subspaces of EP. And for example, think of them as having dimension logarithmic. And these are going to be sampled IID as well. The idea is going to be, instead of giving separating hyperplanes from EP, we're going to try to give separating hyperplanes from these probing subspaces that have low dimension and hence reveal little information about the subspace. So this is how it works. For each layer, we're going to have these probing subspaces for the corresponding subspace at the corresponding depth. And what we're going to do is exactly what I just mentioned before. Instead of testing whether a query is perpendicular to EP, we're just going to test whether it's perpendicular to the probing space. So here is a quick example. Let's say we have a new query. There is a first test, which is just to make sure that the query is not close to the origin. So we can omit this. What we're going to ask is, starting from the first layer, we're going to ask whether it's perpendicular to all of the probing subspaces up to the parameter delta 1, the parameter of this depth. If that's the case, then we go to the next layer and we ask the same question, but for that layer. And let's say it was not the case, then what we're going to do is we're going to return a separating oracle, a separating hyperplane, sorry, but specifically for these, for the probing subspaces of that layer. Okay, and let's say it passed all the probes, then let's say it passed all the probing subspaces up until the last layer. We're just going to say, okay, the oracle returned success and the point is feasible. Okay, so this is for a form of the separation oracle. Now, it turns out that you also need to make sure that these probing subspaces vary over time, because remember that there are two kind of features we need them to have. The first one is that even though the algorithm may have some prior information on the problem, so potentially prior information on the subspaces, we still need to make sure that it needs to explore lots of different dimensions of the previous layer. So the way we do it is by updating probing subspaces from time to time. And more precisely, what we're going to do is we're going to keep track of some so-called exploratory queries. And a depth P exploratory query is essentially going to be the time when the algorithm was forced to explore a new dimension at layer P. Okay, and the idea is that whenever the algorithm makes a new exploratory query, we're going to add a new probing subspace. There is only one caveat, which is we don't want to add probing subspaces all the way. We just want to make sure that the algorithm is visiting sufficiently large number of dimensions at a previous layer, which is parameterized by some parameter k. And so what we're going to do is whenever the algorithm did make k exploratory queries, then we can just restart everything. Okay, so pictorially, this is what it looks like. We have this new query. Let's say it passed the probes at layer 1. What we're going to do is we're going to ask whether it's an exploratory query or not. And this is done by just checking whether it's essentially independent from the previous, linearly independent from the previous queries, which is going to be our proxy for exploring a new dimension of that space. Okay, so as you can see here, we're looking at the span of the previous exploratory queries. So let's say this was the case, then we can say, okay, this is a new exploratory query. And let's say that the layer was not full, meaning we didn't have k probing subspaces. what we're going to do is we're going to sample a new probing subspace and add it. So we call it Vn1 plus 1. And as you can see here, we are going to increase the size of the layer. Okay, there is only one other edge case, which is what if the layer is full? In that case, what we're going to do is we're just going to sample a new subspace V1 and then restart from there. Okay, so we restore the layer. Okay, so this concludes the construction of the whole hard class of feasibility problems. And now I can go very briefly over the proof structure. At each layer P, there's going to be this behavior. First of all, every time we're constructing K probing subspaces, so every time we are adding a new probing subspace, essentially the goal is to show that the algorithm, in order to make a new exploratory query, has to explore a new dimension of that space. So the whole the goal is to show that to obtain all these exploratory queries, we have to reobserve essentially all the subspace EP minus 1. And remember that this is a pretty large subspace. It was a dimension D over P, so basically O of D. And to reobserve a whole subspace, we essentially need to find a vector according to each one of these dimensions. So what this means is that we're going to have to do essentially D exploratory queries at a previous step. Now, the only way that we can get to observe these exploratory queries is through the probing subspaces that we get. And remember that there were K probing subspaces for each step. So essentially, this is going to show that we need to solve the depth P minus 1 problem this number of times, essentially D over K. Okay, so if you combine everything like this, then you can go all the way up to the first layer, and this gives you an exponential query lower bound in terms of the depth P. All right, so this concludes everything I wanted to mention. So in conclusion, we have these lower bounds that essentially go all the way from gradient descent to cutting planes. So there are some natural questions from here. The first one is, we have this discrepancy between randomized and deterministic algorithms. So is there a way that we can have lower bounds for randomized algorithms that go also all the way to cutting planes in a similar manner? Secondly, of course, we want to understand whether we can get such lower bounds for convex optimization. Thank you very much.